Hi, it's Tom and Rob here, and we're delighted to bring you this latest HGView Showcase webinar, this time brought to you by Parker Hannifin.
We are indeed. Now, we've discussed mobility a number of times throughout the year, Tom, and we often find that the undercurrent is all around the investment and the components behind the mobility infrastructure.
Yeah, it really is. So looking forward to getting into this discussion. Over the course of this webinar, we're going to hear all about hydrogen market drivers and trends, an overview of hydrogen refueling stations and dispensers, the challenges of working with hydrogen, and the criteria for selecting the right components for your dispenser. So it's going to be really interesting to get into this.
It will indeed. I think this is an important learning to take forward, as we said, about those components behind the dispensers, about the criteria for selecting them and why, really. So I really look forward to getting into that discussion.
Absolutely. So with that, it's over to our hosts today, Stephen Lerney, Steve Juricki, and Neil McPherson.
Hello, everyone. Thank you for joining us today to discuss selecting the right components for dispensers in a hydrogen refueling station. During this webinar, we will cover a brief market overview, the subsystems that make up a hydrogen refueling station, industry challenges that affect component selection, and various product solutions. Today, you will hear from three of our hydrogen experts, Stephen Lerney, Steve Juricki, and Neil McPherson. Following a career start as an R&D scientist with Procter & Gamble, Stephen then joined GE, progressing through international roles in sales, marketing, and product management. In 2006, he joined Haskell, a division of the Ingersoll Rand Corporation, becoming vice president and general manager in 2017 until his retirement in December 2022. Stephen holds a degree in applied chemistry from Northumbria University and a diploma in business administration from Durham University Business School. Steve is an expert in fluid conveyance products and channels across a variety of mobile and industrial markets with 34 years experience. He currently leads a team across Parker to develop the products needed to build a bridge from natural gas to hydrogen. Neil has over 25 years of experience in sales and marketing, with a focus on developing and expanding alternative energy markets. As the Filtration Group Alternative Energy Manager at Parker Hannifin, Neil oversees the strategic planning, product development, and market penetration of filtration products, which can support a broad range of alternative energy applications, including hydrogen. And with that, I will turn you over to Stephen Lerney to discuss the market overview and trends.
Good morning, afternoon, and evening, everyone. My name is Stephen Lerney, and I've been directly involved in hydrogen refueling since 2012, when my business, Haskell, built our first hydrogen refueling station. I then went on to create a division of the company called Haskell Hydrogen Systems in 2017, that today is building refueling stations and equipment that is in operation all over the world. I retired at the end of last year, and I'm pleased to use my time now to promote the cause of clean energy, and in particular green hydrogen as a fuel. It's my pleasure today to give you a high-level perspective of hydrogen refueling, starting with the market, then introducing you to the key characteristics of a refueling station, and finally a quick look at some of the related challenges of working with hydrogen before I hand you to our much more expert fellow panelists, Neil McPherson and Steve Juricki. Before diving into the main subject matter, for a bit of fun, please take a look at these pictures and the question I pose at the bottom of the screen. A popular lament of today's Luddites is that it will take decades to remove fossil fuels from transport. Whilst I agree that the transition will not be overnight, I disagree that it might take multiple decades. And let me leave you with the comment that change can be quick in the right circumstances. The answer to the question is that there are only 4 years between these two images. Having accepted the premise that the days of mass transport based on fossil fuels are coming to an end, the next frequently posed question is what cleaner technology is going to win. In particular, will it be hydrogen-powered fuel cell electric vehicles, or will it be battery-powered electric vehicles? And of course, there are other technologies being researched, but are not as progressed or proven yet. Fuel cell electric vehicles have the benefit of longer range, already equivalent to today's cars and light-duty vehicles. and development is progressing to achieve equivalence for heavy goods vehicles. Similarly, filling your vehicle takes only 3 minutes for hydrogen cars, and progress is being made for fast filling of larger vehicles. And studies have shown that the environmental impact of fuel cell electric vehicles is lower than that of battery electric. But battery electric vehicles have their own positive features. For their size, batteries have a higher energy density than hydrogen gas. Today, the total cost of ownership to the public is lower than that of FCEVs, though progress with FCEVs is expected as production volumes increase. And there are more charging points today than there are hydrogen refueling stations. That said, my personal view, and that of many others, is that both technologies have a part to play in a cleaner future. Hydrogen for longer range and heavier loads, battery for commuting. I mentioned that there are more electric charging points available than refueling stations for hydrogen. Mainly that's down to hydrogen refueling technology being much less mature than the distribution of electricity. It's actually only 12 years since the first public hydrogen refueling station was opened at the Honda car factory in the south of the UK. In the years following, growth in stations was slow until commercially available fuel cell vehicles began to emerge in volume from 2014. Since then, growth has been steadily increasing, and by 2021, this was the world picture of stations with, as you can see, Europe and Asia, particularly Japan and South Korea, leading the way. And since 2020, apart from a COVID blip, openings are accelerating with 130 opened in 2022, over 300 this year, and growth forecast to achieve a compound annual growth rate of almost 40% through the rest of this decade. The USA is expected to become increasingly important, with some forecasts of over 4,000 new stations to be opened by 2030. Let's take a look now at the basics of hydrogen refueling station design. The image here depicts a station using hydrogen delivered as gas from a tube trailer, pipeline, or electrolyzer. But it's worth noting that stations supplied with liquid hydrogen have only minor differences in technology, with technology downstream of vaporization being identical to gas. There are 6 major subsystems to a refueling station. You can see them labeled here: the gas offload panel, storage, compression with cooling, pre-dispensing chilling, and dispensing. The green arrows highlight the points where hydrogen is transferred between the subsystems. Starting with the offload panel, this is where the gas is passed from the delivery source to the station low pressure storage. Low pressure gas is then transferred via a chiller to the compression system, which raises the pressure to around 7,000 psi and or 14,500 psi, depending on the type of vehicles being refueled. When you begin to refuel a vehicle, gas from the highest pressure storage vessel is transferred through the dispensing chiller to the dispenser and the vehicle. This is referred to as a cascade filling system and is used on virtually all stations. Let's take a quick look at liquid hydrogen, and the chart here shows high-level pros and cons. While liquid has benefits of high purity and higher energy density than gas, and therefore lower associated transport costs, the cons, cost of production, very high hydrogen losses during storage and transport, and factoring in that today's global capacity for liquid is under 300,000 tonnes per year, and the demand for transport alone is forecasted over 3 million tonnes in 2030, I believe it's unlikely that in this decade, liquid can be a viable solution for mass transport. Now let's take a look at some key properties of hydrogen affecting station design and technology. Starting with flammability and embrittlement. Hydrogen is the smallest and the lightest molecule and is normally a gas. Any hydrogen leak is likely to fly up into the atmosphere, unlike liquid fuels. That said, if the leak can't escape, an atmospheric concentration of 4% is sufficient to ignite if exposed to a spark or a flame. Level 1 mitigation is stop the leak. Use components and assembly processes that minimize the risk of leaks, for which I'm sure my fellow panelists will give you plenty of ideas later in the presentation. Level 2 is to detect leaking hydrogen, about which Steve is going to share with you some exciting news of technology. Level 3 mitigation is to use a station design that allows any leaked hydrogen to escape to atmosphere, an effective but not particularly environmentally friendly solution. Turning to embrittlement. Embrittlement occurs when the hydrogen molecule finds spaces in the metal structure, over time resulting in a loss of ductility and increasing the risk of cracking. Again, Steve will talk later about key steps to take to mitigate the risk of brittle failure in metal components. A lesser-known characteristic of hydrogen is the reverse Joule-Thomson effect. The Joule-Thomson effect describes the behavior of gases or liquids when being throttled through an orifice. Unlike all other gases, hydrogen, helium, and neon heat up instead of cooling. In the case of hydrogen refueling, this effect is observed when the gas passes through the dispenser nozzle and into the vehicle tank. Fuel tanks on today's vehicles have a maximum allowable temperature constraint of 85 degrees centigrade. Consequently, there are several technology demands on the dispensing process and equipment, which Neil will expand upon during his presentation. And with that, thank you for your interest. I will now hand you to Neil McPherson.
Thanks, Stephen. Today we're going to talk about some of the challenges facing the hydrogen refueling industry. Let's start by considering hydrogen gas quality. When it comes to hydrogen gas quality, there are well-established international standards which specify the quality of the gas. These are SAE J2719 from 2020, entitled Hydrogen Fuel Quality for Fuel Cell Vehicles, and also ISO 14687 from 2019, entitled Hydrogen Quality Requirements for PEM Fuel Cell Vehicle Applications. Specifications for hydrogen gas are the same in both standards. Each standard details the target hydrogen gas purity and includes a list of impurities which may be present with a corresponding maximum permissible level. It's important that hydrogen quality is maintained at a high level, as certain components may poison the proton exchange membrane-based fuel cell, gradually reducing efficiency and in the long run even resulting in catastrophic failure. Here's an example of just one contaminant, that would be water vapor. According to both international standards, the maximum allowable level of water vapor within the hydrogen gas should be no more than 5 ppm. Elevated levels of water vapor in the hydrogen can cause problems with the refueling process, damaging key components, which may ultimately lead to a catastrophic failure of the system. Furthermore, gas contaminated with excess amounts of water may cause problems within the fuel cell system itself, leading to similar consequences. Hydrogen gas quality starts with the source of the gas. Hydrogen gas may be sourced from several different production processes. Grey hydrogen, shown on the left-hand side of this slide, is the most common form of hydrogen. It is generated from natural gas or methane through a process called steam reforming or steam methane reformation. Hydrogen is labeled blue or blue hydrogen whenever the carbon generated from the steam reforming process is captured and stored underground through industrial carbon capture and storage. Blue hydrogen is therefore sometimes referred to as carbon neutral, as the emissions are not dispersed into the atmosphere. Green hydrogen, also referred to as clean hydrogen, is produced by using clean energy from surplus renewable energy sources, such as solar or wind power, to split into 2 hydrogen atoms and 1 oxygen atom through a process called electrolysis. With all these processes, the gases will contain different types and levels of contaminants. It's therefore important that the correct gas purification solution is installed to ensure that the required gas quality is achieved. Hydrogen gas from the source needs to be transported to the refueling station. There are various delivery methods, including road delivery, trucks with tube trailers containing the hydrogen gas pipeline, or even on-site gas generation using an electrolyzer. Through each of these delivery methods, there could be the potential for contaminants to be introduced. Also, as the hydrogen is being processed through the station, there could be the potential for further contamination to be introduced from, say, storage tanks, or even during the compression process. Gas quality measurement throughout the process is therefore recommended, and of course further purification systems may be required to mitigate risk. Every day, Parker filtration engineers help customers to protect and purify their production processes. The need to mitigate risk and to ensure that high quality gas is continuously delivered to the application, in this case a fuel cell based vehicle, is one which is familiar to us. When thinking about this, I was reminded of the beverage industry, where the quality of carbon dioxide is of paramount importance. Over 25 years ago, Parker developed an incident protection system for carbon dioxide. And you can see from this diagram that the system is installed at the point of use, so right at the end of the gas source, the transportation, and the gas distribution process, just before the gas is delivered into the bottling plant and into the beverages which are ultimately being sold in the supermarket shelves for our consumption. The bottling plant owners have complete peace of mind, knowing that even if there is a quality excursion, any contaminant will be captured by the Parker technology, which incidentally was designed to cover a broad range of contaminants. Let's now move on to discuss the importance of chilling. My colleague Stephen Lerney earlier mentioned that hydrogen gas behaves a little differently from other gases. He also referred to something called the reverse Joule-Thomson effect. Without going into too much detail, I can tell you that the Joule-Thomson effect describes the temperature change of a gas when it is forced through a valve or a porous plug. All gases except hydrogen, helium, and neon cool upon expansion by the Joule-Thomson process when being throttled through an orifice and then expanded. Hydrogen gas, as we know, behaves differently. Instead of cooling, the gas heats up when it's expanded. For example, during the refueling process, when the gas enters into a storage tank on a vehicle. Controlling the temperature and the cooling is therefore a very important consideration within the hydrogen refueling station design, and specifically within the hydrogen dispense process. Correct control and correct cooling will ensure that the process is a safe and reliable one. Over many years, SAE has developed a standard or protocol for refueling which all hydrogen refueling station manufacturers must adhere to. SAE J2601 is the fueling protocol for light-duty gaseous vehicles, and its sister or brother protocol J2601-2 refers to heavy-duty vehicles. By following and implementing protocol J2601, system safety limits are maintained. As you can see from this slide, there is a clearly defined temperature range from -40°C up to a maximum of 85°C. Hydrogen gas temperature is controlled throughout the dispense process. The system takes into consideration the initial temperature of the gas within the storage tank on the vehicle, and also the temperature of the gas throughout the dispense process. By controlling the temperature and also the rate at which the gas is being dispensed into the vehicle, not only will the process be completely safe, but it will also deliver the desired customer refueling experience. The SAE J2601 protocol uses a pressure-targeted fueling or a lookup table approach for 35 megapascals, 350 bar, and 700 megapascals, 700 bar fueling. You can see here on the slide there's a lookup table on the right hand side. These lookup tables are used by the manufacturers of the refueling stations to program the dispenser's PLC, process logic controller, to control the fueling process. The lookup table, the data within it, includes 3 different refueling stations. T40 station refers to the temperature of the gas at -40°C. T30 refers to gas being delivered at -30, and finally a T20 station will dispense gas at -20. Each use different gas cooling temperatures or T ratings to offset the heat of hydrogen compression. The system also takes into consideration additional data inputs. So, for example, it will consider the initial gas pressure from the fuel cell vehicle when it pulls up to the station. It will consider the ambient temperature, and it will consider the dispenser's T rating to determine the fueling rate and the target pressure at which the dispenser stops fueling. Here on this slide, we're just trying to visualize the inputs and the outputs. So clearly on the inputs, you have a refueling station. Depending on which type, T40, T30 or T20, you have different hydrogen gas delivered temperature ranging from -40°C, -30 and -20. And then on the right hand side you have the output. There's obviously a vehicle with a completely refueled hydrogen storage tank ready to do the next 1,000 kilometers hopefully. In the middle you can see the lookup table. That really is that's just the parameters which are programmed into the refueling station's process logic controller, the control system. And as I mentioned previously, the system does take into consideration a number of parameters, including the initial gas pressure when the vehicle pulls into the station, the nozzle, the hydrogen refueling nozzle is inserted into the receptacle. Information will be relayed into the dispenser related to the initial gas pressure. That will be taken into consideration and processed through the control system, as well as things like the ambient temperature and the delivered gas temperature. The whole system is controlled. As I mentioned previously, we want to give the customer that pulls onto the forecourt to refuel their vehicle or truck with hydrogen. We want to give them that experience of a 3 to 5 minute refuel time. The protocol, the hydrogen refueling protocol, derived from the J2601, will give all the required information to control the process correctly and safely and lead to that positive outcome. From a Parker perspective, we provide cooling, so cooling within the refueling station for the process, so making sure that when the gas is compressed, that process is maintained and cooled correctly. And then on the dispense side, we have a range of printed circuit heat exchangers which can operate at high pressures. And finally, we do also have a range of purification solutions. So hopefully we'll find that section of interest. I'm now going to hand over to my colleague Steve Duricki to run through some of the other challenges within the industry. Thanks very much.
Thank you, Neil. Continuing on with some of the industry challenges, I'm going to cover next material compatibility, speed of refueling, some of the pressure ratings that are required, and then also certifications and testing. The main issue with material compatibility is hydrogen embrittlement. Hydrogen embrittlement is a localized form of corrosion. It causes a loss of ductility and a reduction in the strength of the material. And it can occur both in the gaseous form of hydrogen as well as in the cryogenic liquid form. Materials that are compatible with hydrogen, some stainless steels. For example, Parker recommends that you use a minimum grade stainless of 3/16 or 3/16 L. And then there are certain polymers such as PTFE and PEEK that are also compatible. However, there are several materials that are not compatible with hydrogen. For example, some of the softer alloys like copper, brass, some types of elastomers, and plastic. There are several things you can do to help prevent hydrogen embrittlement. For example, material selection. Like I mentioned, with regards to stainless, you want to use a higher grade, 3/16 or 3/16 L. You want to make sure that you have a reputable supplier, one that is using some of the latest processes and can trace that material. Once you have the material in-house, you want to make sure you're using safe and reliable equipment to machine the fittings or the components, quality processes, and you want to make sure you don't add any stress to the components. The design of the system is also critical. You want to make sure you reduce any type of overloading, that you use assembly processes that can be repeatable, and reduce the number of leakage points. And finally, with regards to the process optimization, once your hydrogen system is running, you want to make sure you monitor the temperature and the pressure to make sure that it is maintained within the system parameters, monitoring the media, and in general the system. And there's a variety of different types of sensors that you could put into your system to do that. And I'll talk about some of those later. The next industry challenge I'd like to discuss is the speed of refueling. It's important that we give today's users the same type of experience they have refueling a diesel truck. Current industry refueling takes place at about 3.6 kilograms per minute, which is fine for a passenger vehicle. However, as we move forward to the larger heavy-duty Class 8 trucks, we need to be able to refuel somewhere between that 10 to 15 minute mark. So therefore, the future state, we need to reach refills of approximately 10 kilograms per minute. To accomplish that, Parker is introducing a half-inch high-pressure hydrogen hose that can handle up to 10 kilograms per minute. We will be launching that product in early 2024. Pressure is another challenge for the industry today. Because we want to give that user the same amount of range they have with their diesel truck, we're going to have to increase the pressure that hydrogen is stored on board. Because hydrogen doesn't have the energy density that diesel does, that requires some significantly high pressures for the gas stored on board. Examples of those pressure ranges include 350 bar or 5,000 psi, typically used for smaller class 4 to 5 and material handling vehicles. The higher pressure 700 bar or 10,000 psi systems are used in some of the larger heavy-duty class 6 to class 8 trucks, as well as some of the passenger vehicles you see today. Ultimately, though, to get to those higher pressures, you'd need to be able to handle a system pressure up to a maximum of 1,000 bar or 14,500 psi. And finally, I'd like to talk a little bit about some of the certifications that are available today and some of the testing that is being done. As you can see in the table, there are a variety of ISO, EN, and CSA standards available in the industry today. Some of these are currently under revision, while others have been recently updated and published. The standards apply to some of the key components on a hydrogen refueling dispenser. For example, the hose and hose assembly would apply to a CSA HGV 4.2 standard that is being typically deployed in the US, while in Europe they're finishing developing the ISO 19880-5 standard. A lot of these standards require hydrogen testing. Most of that testing today is done in external labs around the globe. However, Parker is beginning to develop some of that testing capabilities internal. Parker also has several engineers that participate across many of these committees, making sure that there are some commonality between the different standards. Depending on the material and the component, there's a variety of different tests that need to be performed. For example, on many of the metallic and non-metallic materials utilized in a hydrogen system, you'll see both static and cyclic hydrogen exposure tests, tensile strength and fatigue, permeation, and hydrogen embrittlement testing, as well as hardness and explosive decompression. Some of the testing with regards to the components, whether that's valves, regulators, or fittings, would include leakage and permeation, hydrogen and nitrogen pressure cycling, as well as overpressure and burst testing. Rapid decompression, extreme temperature exposure, and of course, some of the environmental requirements that you would see, for example, vibration in salt spray. Parker offers a variety of conveyance and control products for your hydrogen refueling station, whether that includes the high pressure to medium pressure cone and thread connection, as well as an MPI double ferrule compression. We also offer an O-ring flat face connection called Seal Lock for hydrogen, as well as the hydrogen refueling hose in both the 1/4 inch, which is typically used in most stations today, as well as the soon-to-be-released half-inch, high-flow, high-pressure refueling hose. With regards to valve and sensors, we offer both manual and actuated needle valves and ball valves, check valves, relief valves, inline filters, pressure gauges, and sensors. Just to feature a couple sensors, we have a hydrogen pressure sensor that can handle up to 1,000 bar, as well as a recently released hydrogen detection sensor. We also offer manifold valves to help reduce the number of connections in your system, as well as double block and bleed valves, adapters, and a variety of different types of fittings and tube lines. Parker also offers a wide range of filtration technologies to support hydrogen refueling station applications. For cooling, we have a range of process chillers and printed circuit heat exchangers. And for gas purification, we have a wide range of filtration and absorption technologies, which can be customized according to the customer's need. We feel Parker is well positioned for this technology transition. Whether that's the decades of experience our instrumentation team has had dealing with hydrogen, as well as the past decade of some of the compressed natural gas refueling stations that we've helped build across the globe. A lot of that experience in dealing with high pressure methane has given us a head start to develop some of those products now for even higher pressures and utilizing hydrogen. That has really allowed us to develop a full breadth of product for your hydrogen refueling stations, whether that includes the conveyance, the control, the filtration, and the cooling of hydrogen. We have many engineers that participate on some of these industry standards that are either recently been developed or are currently being developed, and have a dedicated team at Parker focused on some of the newer products that are being developed. We'd like to offer some of that engineering expertise as well as our product line to partner with you to help build out some of these new technologies needed for this exciting industry going forward. And with that, I'd like to just open it up to any questions. And again, I thank you for your joining the call and your participation today.
Well, thank you for that very informative and interesting presentation, Stephen, Neil and Steve. And I'm delighted to say that the three of them join us live for an audience Q&A too. So if you do have a question that you'd like to put to the Parker Hannifin team, then please do send it in and I'll do my best to get it answered. Now, to open things up, your presentation was titled Selecting the Right Components for Dispensers in a Hydrogen Refueling Station. Is part of the correct selection process down to the region and differing regulations around the world, possibly? Is there regional considerations that you need to make? I'm not sure who wants to take that.
I can talk to a little bit of that. There are indeed differences. For instance, in Japan and some other parts of Asia come along, there is a demand for a high nickel content on steel, on wetted steel which is going to come in contact with hydrogen under pressure. Other than that, the variations that you see really are around the same kind of variations you'll see on chemical plant or production plant, electrical standards, the electrical IEC X versus ATEX, those kind of things. But from a material point of view, that's the only major one really that you come across as a variance.
Thanks for that, Stephen.
Sorry, I was just going to say from a filtration perspective as well, we would have similar considerations around the pressure, approvals relating to pressure holding vessels, and also electrical standards, but pretty standard within the industry. Yeah.
Perfect. Thanks for that. And Stephen, coming back to your point on materials, we've had an audience question wanting a bit of clarification on the materials used for various parts of the dispenser. I'm not sure who can answer that.
I'm not really sure what the question is. There's because of the pressures, you've obviously got significant amounts of material capable of withstanding either 500 or 1,000 bar within a dispensing flow path for hydrogen gas. Other than that, I think what Steve talked about really in terms of material selection, there's steel obviously forms a huge part of it, but there are also some flexibles in there, and then there's various polymers which are favoured for a variety of reasons. So PEEK in particular, I think Steve referenced as very suitable in that kind of environment. Steve, I don't know if you want to add to that. You're on mute.
I mean, you kind of covered as far as this, hydrogen, brittlement, it's not just any type of stainless steel. We rely typically on 3/16L, or like in your case, you mentioned some areas where they're even actually looking for a higher nickel content. So, but there's a lot more to just the material selection, right? We're talking about, and I think I covered some of those areas to make sure that the material is traceable, to make sure that the parts are machined properly, that the system is optimized, and that the system is also maintained. All of that, I think, can help eliminate any concerns with regards to hydrogen embrittlement. So.
Sure, thanks for that, both of you. Hopefully that's answered that particular audience question. Now coming to another audience question. What kind of seals, leak detection and thermal insulation systems are used for hydrogen?
I can't really talk to seals. We did talk about PEEK and I think PTFE seals in some systems, but steel seals as well. The leak detection, there's a range of solutions around leak detection, although up until the one that Steve presented to you, most of those were based around detection of flame, which is kind of after the event, as opposed to the actual detection of hydrogen.
Sure, thank you. Tricky question, I'm sure. How do you at Parker keep developing upon your products? What's next? Is it higher efficiencies? Is it continued cost reduction? Where do you go from here?
I can probably speak to that. Generally, the development process is aligned to customer needs. So we invest quite a lot of time in working with our customers. We use a process called new product blueprinting, which really aims to identify pain points or challenges within the industry. So we consider the voice of the customer. We look forward to and participate in certain like regulatory bodies, bodies that are establishing new standards, and obviously we make sure we're developing products which comply to not just customer needs but also any future legislation standards that may be coming through the pipeline, so to speak. From my perspective, the biggest thing is understand the customer pain, getting close to customers, understanding exactly what they require, and then developing an optimal solution for them that adds value and enables them to run the system more efficiently. We can also at Parker, because we've got such a broad portfolio of products, we can also have the advantage of linking certain Parker technologies, and then developing a package which adds additional value for customers. So from a filtration perspective, we're probably one of the broadest portfolios on the market with all of the core technologies. So we can offer cooling, we can offer dehydration, we can offer heat exchangers, we can offer the whole package. And in having control of those assets, we can come up with something unique and value added.
Sure.
If I could just add a little color as well. So we've, with regards to compressed natural gas, right? CNG refueling dispensers and opportunities. So we've had 15 to 20 years working in those applications, right? So we're dealing with methane at 3,600 psi. We were able to take a lot of those same products, both conveyance, control, and filtration, and obviously we're dealing with higher pressures, but we pretty good, solid, robust product line to start off with. So, and we learned a lot about handling gas in those applications in the past. So I think that's also helping us bridge a gap to hydrogen. So that's definitely speeding up the process of some of the development of these key products that are needed.
Absolutely. So following on from that, you're really leaning on these lessons that you've learned with previous systems, previous gases to aid you here.
Yes. Yep.
Audience question here. What's the difference between handling liquid hydrogen and gaseous hydrogen? They've got their separate challenges. So what's the difference?
You want to take that, Stephen, or you're on mute?
Yeah, it'll be a better answer if I'm off mute. Yeah, I'll take it from a higher level, Steve, and then as opposed to component level, and pass it to you. So certainly from a high level, the fundamental is first of all the temperature that you've got to have liquid at all. I can't remember the exact number. I think minus 253. So no matter which way you look at it, extremely, extremely cold, and with that comes a lot of challenges in terms of stopping it from warming up, because when it warms up, it turns into a vapor, and then that vapor, like hydrogen gas, looks for ways of escaping. But then as you want to move the hydrogen, the liquid hydrogen, either loading a tanker or unloading a tanker and moving it through another system in the station, then all the equipment that you've got associated has to be capable of working with a product which is so cold. So that's the first challenge. And that puts a lot of constraints on the material that you choose to use with hydrogen and the design of these components as well for functionality. Downstream of liquid getting onto the station, today, I think maybe all, but certainly the majority of stations will take the liquid, put it through a thing called a vaporizer, and turn it into gas. And then from that stage on, the station, in terms of design and components, is exactly the same as the design of every other gas supplied station.
Yeah, the only thing I could add to that a little bit is, like I mentioned with compressed natural gas, we've also been dealing with liquefied natural gas. So again, the materials, some of the pressures, obviously, if you're pressurizing gas, you're at a much higher pressure. When you're dealing with liquefied gas or liquefied hydrogen, in this case, you're dealing with lower pressures, but at much lower temperatures, the minus 253 centigrade that Stephen mentioned. So they're both pose different challenges. At this point in time, we've seen more opportunities, more vehicles, more OEMs looking towards compressed gas, since we're still a little bit behind with regards to some of the development of some of the products needed for liquefied hydrogen. But ultimately, in the long run, to get the volume that you need, especially when we're talking larger vessels like ships or rail, you're definitely going to deal with liquid hydrogen. So.
I think it's worth adding that Parker is dealing with both today. So it's within Parker's wheelhouse to handle both liquid and gas.
Absolutely, thanks for that, all of you. Now we've got a few technical questions coming here, so we can rifle through a few of these. Do you see station pressure going above 1,000 bar in the next few years?
I personally don't. There has been some discussion about it going over 1,000 bar, but if you want my really is a personal feeling on this, the cost jump going even from 350 to 700 bar and everything associated to how you manage a system working at those pressures was significant, and so hydrogen refueling stations today is not a cheap item. If you go up in pressure, you're going to increase those prices again. So I don't see it being a significant change in the near future, anyways.
Sure, thanks for that, Stephen. Now another one. What is the mass flow meter used for hydrogen dispensers?
That's out of my knowledge level, that one. Sorry. We can do some digging and find out if the questioner has left that question behind, and his contact details. We can get back to him, I'm sure.
Ari, perhaps if you reach out to the Parker team, they'll be able to answer that one for you. A question from me. It's a topic which comes up a lot on HTV webinars, and we only heard last week in one of our own events. One of our speakers said that the public are scared of seeing hydrogen tanks above ground. This has got to be a consideration for you in refueling stations. So is perception still a problem in this industry?
Again, let me answer it from a kind of high level that I've observed as someone deploying stations. I haven't heard too much pushback from the public. There's been some concerns around noise. When a station is actually being tested, you go through a vent test, and that can be quite noisy. So that's raised a few concerns, but never anything about tanks. But most stations that are out there have the storage for hydrogen is behind either a wall or some other kind of barrier. So that's how, in most cases, that's how they're being deployed. At least the ones in public spaces, not so much the ones which are on private property, but in public, I remember going to China and seeing they had some fairly tall, they had tanks, if you like, on the vertical as opposed to on the horizontal, and they were visible. But quite honestly, they just look like the kind of tanks that you see where you pass any kind of hospital or chemical plant. So I don't know that they would cause any concern. Having said that, I think the industry has to continue to work on its PR to make sure that the public is kept we just keep them appraised of what's going on, and do whatever is needed to make sure people have enough information that they're not getting concerned about what's going on.
Absolutely. Would anyone else have anything to add on the case of perception?
I think I would just echo Stephen's comments around just increasing awareness within the general public. Certainly in the UK, watching the TV and the BBC news, there's been a lot more. It's noticeable. There's a lot more articles around the use of hydrogen and hydrogen powered vehicles, and also some good publicity by certain city councils in the UK that have invested, that have refueling stations. I think it's the transport that's being fueled by hydrogen is quite clearly labelled for being used with hydrogen: buses, taxis, other municipal vehicles. And I think I visited a refueling station up in Aberdeen, and that was actually quite near the like a highly a highly populated area, and obviously that's been running for quite a few years. And I think that the Aberdeen City Council have done a great job to explain what was going on and to increase the awareness. And obviously those buses and trucks and other vehicles are running around the city without any problems, and making people feel more comfortable with the technology and with the gas.
Sure, thanks for that, both of you. Now, we are slightly running out of time here, so I'm going to come back to you for one final question. What would be your message to the people watching today that you would want to get out from yourselves?
Well, I'll go ahead and speak first here. As far as even the last slide when we wrapped up, I mean, there's a lot of people out here on a line that'll be looking at perhaps building dispensers or stations. Parker, with our capabilities in fluid conveyance, control, and filtration and chilling, we'd like to just reach out and offer some of our expertise, whether that's engineering or product, to work with you to help further develop the proliferation of hydrogen refueling stations. So if anything, I'd like to leave that message and offer our availability, and obviously our contact information will be provided as well.
Sure. Thank you, Stephen.
Yeah, I just harking back to your previous question about PR, and also building on what Steve just said, I think it's critical that the industry, and I'm assuming a number of people on this call are somehow aware, either in or going to be in the industry, really needs to take care about safe practices. And it's critical. It's a young, evolving industry. It would be quite easy to derail if people made some of the wrong choices in terms of design or materials or anything else associated with this. So safety is absolutely, in my mind, is absolutely the prime thing to be focusing on with respect to developing this industry.
Yeah, Neil, I'll leave the final words with you.
I think my colleagues pretty much summed it up very well. I think obviously it's a developing market. We've got to support the new technology as it's developed, but we've also got to get that message out to the public about the use of alternative fuels in like hydrogen in vehicles, and just make sure that everybody feels comfortable with this moving forward. I don't really have any other thoughts just now, aside from repeating maybe what Steve said, that we really look forward to working with you and supporting you with any requirements that you might have or particular challenges with the design and construction of refuel stations. We're here to help.
Well, thank you, Neil. And sadly, with that, we are out of time today. Our thanks once again to Stephen Lerney, Steve Dricke, and Neil McPherson of Parker Hannifin. And that also brings H2View webinars to an end for 2023. But don't worry, we'll be back in 2024 for a brand new programme covering all the big talking points in hydrogen. For regular viewers, you may be used to visiting gasworld.tv to tune in, but from next year, H2View webinars will have a new home. I can't say too much just yet, but do keep an eye on our social channels for updates on that. In the meantime, you can still check out the library of webinars we've previously held. Subscribers to H2View can go back and watch any of those free of charge on gasworld.tv. Do be sure to also visit h2-view.com to stay up to date with all the latest news in the hydrogen industry, as well as various recaps of this very webinar. All that's left for me to say is Merry Christmas from all at H2View, and we look forward to seeing you again in 2024. Goodbye.